بسم الله الرحمن الرحيم مرج البحرين يلتقيان بينهما برزخ لا يبغيان فبأي آلاء ربكما تكذبان يخرج منهما اللؤلؤ والمرجان فبأي آلاء ربكما تكذبان وله جوار المنشآت في البحر كالأعلام فبأي آلاء ربكما تكذبان صدق الله العظيم. Jazakallah. Please hold for a few minutes. There is some audio problem in the coverage. Sir, can you hear us now?
Yes. I can hear you now.
Now I request Professor Dr. Naveed Hassan, Director Institute of Geology, for welcome note to audience and the speakers. Bismillahirrahmanirrahim. It is my pleasure to welcome you all to international webinar on the marine geosciences and quaternary geology. It is a high time to organize such an event that will integrate fresh knowledge and technical contribution on quaternary geology. First of all, I would like to thank the speakers of this webinar for sparing time for this event, especially Professor Dr. Bilal Ul Haq, Professor Peter Clift, and Professor Liu Keyu. This webinar on marine geosciences and quaternary geology aims to bring together leading academicians, researchers, and research scholars to exchange and share their experiences and research results on sedimentary processes during quaternary time. This program will showcase talks on most recent innovations, trends, concerns, as well as practical challenges encountered and solutions adopted in the fields of marine and quaternary geosciences. If you take a look at the webinar program, the talks in this event will cover the specialized field of quaternary geology, the effective benefit from geoscience application. It is essential that geological professionals set themselves ready for transforming their practices and keep identifying effective ways for transformations in their context. In closing, I hope that all of you will enjoy the talks, and I wish your attendance from around the globe, and it will be a very pleasant experience for research exchange. I also welcome the representatives of government and industry associations for joining this event. Thank you very much.
Thank you, sir. Now, without any further delay, we start this webinar. The webinar program is comprised of 5 talks focusing on the quaternary geology and rocks of Macron Basin, Macron Subduction Zone, Tectonic Plateau. It's a derivation of sediments from Tectonic Plateau. And then the Kirther Fold and Thrust Belt, the rocks of Quaternary which were deposited near the Kirther Fold and Thrust Belt. The title of our first talk is New Findings on Tectonic Sedimentary Evolution of Macron Subduction Zone, and the speaker of this talk is Dr. Bilal Ul Haq. Dr. Bilal Ul Haq is a world-famed geologist. He is graduated from our institute, and then he got his PhD from America. He is Pakistani-American marine geoscientist. He has been advisor to World Bank Environment Department, Division of U.S. Science Budget in the White House, UNESCO Intergovernmental Oceanographic Commission. He published classic papers on the topics of paleoclimatology, paleoceanography, sequence stratigraphy, micropaleontology, natural gas hydrates, and past sea level changes. Currently, he divides his time between Smithsonian Institute, Washington, D.C., and the Sorbonne University, Paris. His honors include Sheffield Medal for Excellence in Marine Geology, National Science Foundation's Antarctic Medal, American Geophysical Union Ocean Science Award, and he is elected member of European Academy of Science. Now I hand over the mic to Dr. Bilal Ul Haq to start his talk.
Thank you very much. First of all, let me thank Director Hassan and Dr. Jawad for organizing this important symposium. As you probably have known, my talk is not about geology, but more the development of marine aspects of offshore aspects of Macron as well as onshore aspects. Now, as you know, Macron is a very important area for Pakistan. Its oil industry is really active, has been in the past, we will be in the future. So we need to know more about this area. Very little is known about this area. So anything we find about Macron is going to be new. Some work has been done, but a lot of the data remains in the coffers of the oil industry in some cases, and with some academic data remains unpublished. So this is the first time you will see some new data on Macron, and it's based on a PhD thesis that was just finished only last Tuesday. It was defended successfully in Sorbonne by a PhD student. His name is Dia Ninkabu, and he originates from Palestine, but he is of it's a Frenchman, of course. He's lived all his life in France, so he is a very, very smart and excellent researcher, and he has shed new light on the Macron area. So Macron, of course, those of you who are familiar with it, has been is divided into two parts. We have half of it on Pakistani side, and Iran has the other half of Macron on their side. So there's Western and Eastern Macron, and they have never been studied together. So this is the first time that any researcher has actually try to bring together these two parts and study it as a unit. And it turns out that not only East and West Macron are linked together, have a combined history, but also the northern coast margin of Oman is also linked to this area, because much of the tectonics that happened in the Mesozoic and Paleogene in the Oman have also affected the subduction zone on Macron. So this particular thesis of Dia Ninkabu was actually combine these two areas of East and West Macron as well as the northern margin of Oman. So now I'm going to try and project my slides. I'm not sure whether you're seeing it. Are you seeing it? Is that okay?
Not, sir, not yet.
Okay. I'm also very happy to see that you are all wearing masks. Here in Washington, we have 70% of the people have been vaccinated, but I still go out with masks because it's better to be safe than sorry.
Yes, sir. Also, the vaccine has been started here in Pakistan.
Excellent, excellent. Okay. So, do I press a button here?
No, sir. Please check the button on the left top. It's share content.
Share. Open share. Okay, there we go. Can you see it now?
Yes. Now we can see. Please, sir, you shared the screen or the window?
The window.
Okay.
It's fine.
Okay. It's okay now.
All right. So as I said, this is based on PhD thesis. Mostly the research from Sorbonne University by a PhD student who was working with me and several other professors at Sorbonne. And so, of course, it covers, as I said, both the Irani side and Pakistani sides of Macron, and it also covers northern Oman margins. So there are a couple of papers that have already been either published or submitted. Journal of Geophysical Research, there was a paper published just recently, earlier this year. It's the first one. It's on Oman. Actually, you can see that the abducted margin of Oman, and this was published first because Dia finished his study of the Oman earlier than he did the Macron. And so that was published. And then there is another paper that is now in press, also mostly on Oman and on the Arabian Sea sediments. It's more on the sedimentary side. And then here is his PhD thesis, which was actually defended just this week on Tuesday very successfully in Sorbonne. So nobody has, and of course there are many more papers in preparation on Macron. So nobody has seen this data outside Sorbonne. So you are very privileged to be seeing it for the first time. Now, we call Macron a subduction zone. So I'm sure most of you are geologists, so you know what a subduction zone is. So I thought, just in case, to familiarize you with what a subduction zone is, I just put up this cartoon which shows a subduction zone. Subduction is a geological process in which denser oceanic lithosphere dives below lighter continental lithosphere at plate convergences. So you can have a oceanic continental convergence, or you can have oceanic convergence as well, where you can have an oceanic plate going underneath another oceanic plate. And you can decipher the shape of the zone, this lithosphere going down, oceanic lithosphere going down underneath the continental lithosphere, and you can decipher that by earthquakes all the major earthquakes take place along this subducting slab boundaries, and this is called the Benioff zone. Or Benioff zone is where all the major earthquakes occur in a subduction zone. This produces, of course, a subduction zone. So that's a subduction zone, the whole thing. And then it also produces a trench. This is called a trench. This is the whole thing is called a trench, and then it produces a accretionary prism around behind it. So this is the accretionary prism. This is where the lithosphere is accreting. It's coming together in large amounts, and that's why it's called an accreting prism or accretionary prism. The subduction zones are also characterized by major earthquakes, but not only major earthquakes, but also microseismicity, small earthquakes that are happening all the time. They are so small that you cannot feel them, but they are there. For example, if you put a very sensitive seismometer in Karachi, it will probably be constantly humming with microseismicity because the earthquakes are happening constantly. These are micro earthquakes. They of course, but they are also very important when we study the shape of these subduction zones and the Benioff zones. Fluids are released from the subducting plate, and it triggers volcanism. And of course, you can get volcanoes overriding and on the overriding plate. So this is the overriding plate, this is the undergoing plate, and there you see volcanoes, and this is called a volcanic arc or a back arc sometimes. This is called the fore arc, and this is called the back arc. So these are the terms that are very often used by geophysicists and geologists who are studying the tectonics of these things. The angle of the slab is an important characteristic. If it is shallow, it produces deformation belt with crustal thickening. So there is a very thick crust if it is shallow. But if it is steep, it produces a typical back arc basin here. So Macron is an excellent laboratory to study subduction zone with relatively shallow Benioff zone and major earthquakes generated between 10 and 160 meter depth. So that depth of 10 to 160 kilometers below the surface is a very important zone. It's called the seismogenic zone because that's where most of the major earthquakes occur. Okay, now here is actually a real image from a seismogenic zone or a subduction zone. This is from the Nankai Trough. Some of you may know where Nankai Trough is. Nankai Trough is just along Japan, the east of Japan. That's where the oceanic plate, this one, is undergoing Japan. So that's Japan up here, land is here. This is the Japanese shelf, and this is the accretionary prism, and this is the plate going down. So you can actually see this beautiful seismic, 3D seismics, that these things, the plate is actually subducting down. And this is the locked seismogenic zone where major earthquakes occur. And the Nankai Trough, of course, the Nankai Trough is a major example of this subduction zone. But Macron, of course, is also another type of subduction zone, but it's also a very, very important one in the world of subduction zones. This experiment obtained these very high resolution 3D seismic images, which was funded by US NSF. I used to work at National Science Foundation as a director of marine geosciences, and I was responsible actually for funding a lot of this research in the Nankai Trough when I was there. So I'm quite familiar with this thing. And everything we know, now it was also drilled later on by deep sea drilling program, and as you can see, we had a very deep drill that went right through the place where the two plates meet, right through the accretionary prism into the underlying plate, and there was also some shallower holes were also drilled along the overriding as well as the underplating plate. Now, everything we know about the tectonic facies lithofacies that are typical of subduction zones comes from this particular experiment. Okay, I think I can. Sorry. All right. So you can clearly see the subductor and overriding plates here. All right. Now let's set up the setting of Macron in the global picture of what was going on with the plates that make up the Macron part of Pakistan. Of course, Pakistan is partly on the Indian plate and partly on the Arabian or Eurasian plate. If you go from Triassic, this is from the late Triassic picture, and it is the present day picture, and here's the late Cretaceous picture. If you go from Triassic, the Indian plate was still attached to Indian plate is right here. It was still attached to Gondwana land, and the Neotethys was a big ocean between these bits and pieces of Cimmeria and Eurasia, and then there were two oceans, one called Neotethys, the other called Paleotethys. Together they later on become Tethys. So in the Paleogene, as you can see, that India has now separated, split from Africa, and but Madagascar is still attached to it, but it is moving eastwards, and it's moving actually moved very rapidly. By the late Cretaceous, Gondwana had split, and the rapid movement of India started northwest, which collided with Asia at about 50 million years ago in Eocene. And Tethys Ocean was largely closed by the end of the Paleogene, and the present day conditions actually started somewhere in the Miocene or late Oligocene or Miocene at that time. Notice they reconstruct the spreading ridges. Of course, we reconstruct these spreading ridges based on models, but there is no direct evidence that these were the shapes of these spreading ridges. So these are just conjecture, but it's probably true because you need spreading ridges to be able to split the two plates apart and have them collide with each other later on. Okay, so here is now Macron in this is this study area in this triangle includes northern Oman and Macron, and also land-based sections in Iran and Pakistan, and it is actually a continuous fold belt which goes from the alpine regions of Europe into Asia, and then of course north right here in north of Arabia, and then Iran, and Zagros Mountains up here, and then Indian plate starts here, and the Chaman Fault is the boundary between these two plates. So you can see that it is a complicated area. The upper picture shows you the various plates that are now in conjunction with each other, and the lower figure shows you the tectonic provinces. And here we will be talking about mostly this province, the Macron accretionary prism. Okay, now here again you see setting of the Macron subduction zone and northern Oman margin. I'll be showing you two sections here, and I'll be actually showing you some results from them. I thought it would be a good idea for you to keep an eye on some of these findings early enough, so that when you look at the evidence, then you can see that the evidence is based on these particular seismic sections as well as on these models. So section A and B will be the next two slides. This is the section A, which is northern Oman margin through accretionary prism and this subduction zone right here. So northern Oman margin is here, Oman abyssal plain is here, and then here is the Macron accretionary prism, and this is the land part of that. This is the wedge arc behind it. And you can see, this is based on this summary slide is based on actual seismic data, and you can see that there is a lot of tectonic activity here in the Macron itself. There is also some abduction here of old oceanic crust in the Samail ophiolites, as they are called, in Oman, which are actually have some connection with the older history of the Macron. So here are some of the findings. Key findings of this area is that infill of the abyssal plain is flat lying turbidites, mostly turbidites. Turbidites, as you know, are deposits that are formed by slumps and slides, as well as currents. And they are actually two kinds of these things. They are the ones that are sorted, well sorted, and then of course there are also contourites, which are collected together by currents. So these turbidites were deposited in the early to middle Miocene, and then clastic input from northern Oman during the late Miocene. So there was a lot of sediment coming down from here because this is the high relief area. And development of hybrid turbidite contourite system occurs in the Pleistocene associated with the flexure linked to Macron. So the flexure of Macron itself is causing, and the high areas in Macron are causing sediment to come also from the north, not just from the south at this time. And Pleistocene is deformation of the imbricate fan of Macron accretionary prism. So there's a lot of deformation that happened in the Pleistocene. It started already in the Miocene, but it became more important in the Pleistocene. Now we'll see the second slide, the second section, which goes through the Indus fan area, the distal Indus fan, plus the Dalrymple trough. This is the trough. It's a shallow, and then there is the Murray Ridge, which is a high relief, and then of course the Macron accretionary prism. If you remember, it goes right through those areas. And the findings here are active channel levee system throughout the Miocene in this area, late Miocene deformation since 10 million years of the Dalrymple trough, infilled by clastics from the northern Oman margin and development of contourites, and then intense Pleistocene deformation of Dalrymple trough. This is all Pleistocene, indicated by mass transport complex. So there are these mass transport complexes here and major unconformities, complexes which are overlapping the younger sediments. Okay, now if you look at the Neogene chronology of the Arabia and its surroundings, Macron and India, the Indian plate, you can see that Macron, we don't need to go into detail of this, but just wanted to show you that when you compare these neighborhoods, you see that the Macron is quite distinct from both eastern and western regions in its tectonic history. So it's a unit by itself. It's sitting there. But it has had a very complex history, which you will see in a minute as we talk about this thing. Here are some of the old plate boundaries and the tectonic blocks that play a major role in the Macron subduction zone. And as you can see here, these red areas, these are all tectonically deformed areas. These areas are also highly tectonically deformed, the Macron subduction the subduction zone lies in the transition between two collisional origins. For example, here is right here is the Zagros Mountains, and which is collisional area, and then here is the Kirthar Suleiman range, which is of course another collisional area. So between this collisional origin, Macron is right there, sitting in there, and it is affected by these two origins in its history, and the characteristics of this zone, subduction zone, are very much linked to these tectonic neighborhoods. Now, this shows an integrated structure of both Pakistani and Irani sides of Macron, the western and eastern side of Macron, and some of the major faults that are long-lasting, major faults that run right through the whole system, and also the major tectonic trends. And you can see this is the Indian plate here, and this is the Eurasian plate. The prism as a backstop is a continental block. So this continental block has imbricated ophiolites and continental material in the west. So ophiolites are, of course, old oceanic crust that has abducted now and come up and is visible in outcrops. So this is called abduction. When oceanic crust comes up by tectonic processes, that is an ophiolite. So you can see the ophiolites in the Irani side of Macron, as well as in the Bella ophiolite here in the Kirthar Soleiman range is also typical of this area. These features are absent in the east. These are the imbricated ophiolites are absent in the east. But the backstop here is a volcanic arc, the Chagai Rashgo area, and the Paleogene Sistan suture. Sistan is up here. Suture zone separates both these areas. So that's the Sistan suture and separating the Pakistani side of Macron from, and they are not similar. They are quite dissimilar, in fact, in characteristics. These are some of the physiographic differences from west to east. The western Macron has more chaotic structures. As you can see here, there were lots of chaotic structures and few thrusts, whereas eastern, its shelf and slope transition is gentle. Shelf slope transition is gentle, whereas on the eastern side, Macron has well-defined structure. These are extremely well-defined structure and an elongated thrusts compared to the west. An eastern shelf and slope break is more abrupt. The shelf slope break, which is in here, here, is rather abrupt. It is more gentle here than here. And Zagros influence is called characteristic in the west and Indian plate collision in the east. So these two things you must keep in mind, that these two influences are really important in this area. Okay, now these are some models based on tomography mostly, which I will show in a little while. This is the tectonic evolution of Oman Macron complex, as it's now called, late Cretaceous through Paleogene. And as you can see up here, you have 95 to 90 million years in the late Cretaceous, and then from 90 to 60 million years in the late Cretaceous and late through Paleocene, and then 50 million years to 25 million years, which is Eocene and Oligocene. So you can see that there are multiple subducting plates in the late Cretaceous, not just one, but two. Maybe there was a third one at a tangent to these things. So there are multiple slabs, as they are called. So these slabs are persistent. The evolution of subduction in the area with multiple slabs, the late Cretaceous. And Berg was the guy who looked at the tomography's data from this area, which is very, very recent, only 2 or 3 years ago, and came up with this model. And convergence and abduction along Oman up to Paleogene. So this area was abducted in Oman with possible stalled subduction. There's some stalled subduction here, probably in the forward slab. And then in the Eocene onward, there is a development of the current Macron system, which is you see here now. So these are models that are, of course, based. The evidence is from seismic tomography and This will be the second part of my talk today when I show you that. The model shows that Macron subduction zone is also unique in that the subducting plate is linked to the old Oman margin. That's how it's linked to the Oman. And abduction in Oman actually resulted from the fact that there was a stalled subduction, and when you stall the subduction, you bring out the oceanic crust to the surface on the other side. So that's simple physics there. Now, seismicity or earthquakes are very, very important indicators or evidence in this area. And here are on the Macron itself, more than magnitude 4 earthquakes, which means that medium to large earthquakes only. They are all plotted here. And geodesy, which is the angle at which the plate is moving. So this is GSP velocity vectors. These are you put down seismometers or GPS geodetic instruments that measure the movement of the soil or of the surface of the earth, wherever you put these on, and then you measure them very accurately with GPS, and you can measure them with the accuracy of a few millimeters, and they can show you how the plates are moving today. So these are the movements of the plates right now. All of Pakistan and Macron and Iranian Macron are moving northeast direction, and these, and of course the movement is very, very slow, so you can't actually measure it except with these geodetic instruments. So there are these two cross sections that I'm going to show you, one here and one here, and the upper one is the west one, the western side, and the lower one is central Macron, western Macron and central Macron, and the central one is more towards the east, of course. The upper section is through the western Macron subduction zone, while the lower one is from central Macron. The lower section extends deep into the Helmand block in the north. So this is, although central Macron is still mostly in Iran, and the Helmand block is up here, and it goes all the way. But the study area, the investigated area, is just extends from here to here only. So this area has not been, Helmand block is up here, but we haven't studied that. This is the part that we have studied. Okay, so now I wanted to show you some, also some Benioff zones. The Benioff zone, sometimes also called the Benioff zone, depth along 3 cross sections from west to east. Remember in the second slide I showed you a cartoon of subduction zone, and there you saw a very nice Benioff zones and all the earthquakes. Here is the Benioff zone from west to east. This is west, and this is east, and this is in the center. And as you can see, the shape of the Benioff zone are different. It is quite shallow, but it's also shallow here, but it gets a bit steep later on. There is an older part of the stalled subduction which makes it a little more steeper, but it's also a more recent part of this Benioff zone is also fairly shallow. The subducting angle is shallow in the west and getting a little more steep in the east. Major earthquakes are between 10 and 160 kilometers depth, and that's what marks the Benioff zone, of course. And now here is are the models of active deformation in the Macron area, and as you can see, this is the red color shows the deformation, high deformation quotient, the second invariant, as they called. Second invariant in geodetic models is a measure of strain, and thus active strain related deformation, which is happening here in the Zagros, in the Kirthar Suleiman range, and along Macron, as you can see here. Now this is vorticity. Vorticity is is a whirling, or it is not a simple rotation, but it's more complicated than rotation, but it's also a measure of deformation. And you can see there is a lot of deformation in here in this area, as well as in this area. So the Macron is sandwiched between these two deforming provinces. The Macron as expected, shows strong deformation both along the trench and two ranges, the Zagros and Kirthar, that are bound to it on the west and east. And then, okay, now let's look at some of the stratigraphic differences in the Irani and Macrani side. As you can see, they are different because the backdrop of these two parts of the Macron subduction zone are different. The Irani side is different than the Pakistani side, and stratigraphy is also quite different. The western Irani Macron stratigraphy is comprised largely of volcanic clastics, gypsiferous marls, and carbonates, whereas the eastern Macron comprises largely of contourites, channel levee complexes, more sediments that are derived from and brought down by rivers, and major change in lithology occurs around 11 million years, when there is also major unconformities at that time too. That's where the nature of the lithology changes, and that has to do with tectonics in this area. Okay, now here are two sections that Dia has put together, one from the Irani part of Macron and one from Pakistani part of Macron, and these are amphibious cross section, meaning that they go from ocean to land and ocean to land, and that's why they're called amphibious. The upper section is from western Macron, and the lower one from the Pakistani side, eastern side. Seismic data from the study came from old legacy data obtained by many different companies in Pakistani side. I have to say a few words about the data. Now, the data is available for this study has come from many different companies, and from whom we have permissions to study this, but not to publish some of the lines that they have given us. So when I show you some of the interpretation, I will have to cover the seismic lines up a little bit, because our paperwork is still not complete to publish those things, so we cannot show them. But I can show you all the interpretations. That's okay. But even that you are seeing for the first time. Nobody else has seen them. So seismic data, now on the Irani side, the data was largely gathered by NIOC, National Iranian Oil Company. They contracted it out to many different companies, and this is a good 3D and 2D data. Most of the data in Pakistani side is 2D data, although more recently we have, I hear that we have 3D data as well, but that was not available to us. So it is all based on the legacy data from the companies that they were kind enough to provide us. B is the westward large scale. You can see on it's a large scale on this part of the wedge here is a large scale subcreated thrust sheets. Thrust sheets are landward and imbricate faults. These imbricate faults on the basinward side, and in the eastern on the eastern Macron, you have closely spaced, deep-rooted thrust sheets, as you can see here, so there are these differences from one side to the other as well. Now there is a third section which goes from here to Kirthar range, from Indus side, from Macron side to Indus side, and through Macron range, and which we will also see in the third section here. Here you can see the subducting plate to the west is transitioning to the Indian continental crust, and you can see Kirthar, which is the part of the Indian plate, and it's all deformed and highly faulted, and then crust on the east of the Oman fault, which is somewhere in here. And you can also see the Bella-ophiolite right here. This is sitting right on top of the Paleogene. There's the abducted Bella-ophiolite sitting on top of the Mesozoic strata. So it is actually right here, the black shown here is the Bella-ophiolite. So this is also an important ophiolite example. And the one in one in Oman is very well exposed and very well developed. So that's why when you want to see a good ophiolite, you go to Oman. You don't go to Bella because most of this is covered and it's not well exposed. Although it is also for petrologists, is also heaven sent area, the Bella ophiolite. Now here I'm going to start showing you some cross sections of seismic lines on which the interpretation are actually based. And as you can see, I've covered up the seismic line because we are not allowed to show them as yet. As I said, we will have permission soon, and then we'll publish all of these things. But right now, the paperwork is not complete. But we are allowed to show you the interpretation, which is the important thing actually. That's what you are here for, not for the seismic line. Okay, this is seismic data interpretations. Offshore data shows a gentle slope here and a wider shelf in the west and steeper slope in the east. Okay, so this is the difference that you should keep in mind. Wedge top mini basins, there are all these mini basins on top of the wedge right here. You see, this is the wedge, and I can see all these mini basins in here, separated from the imbricate thrusts. So the imbricate thrusts are right here, and they are the mini basins on top of these things. So individual basins. Plioplastron sediments prograde over the imbricate thrusts. So all of these that you could see here sediments you see in yellow at the very top are the plioplastron, but they bury the faults in the east. Okay, shale diapirs and listric faults are also seen in the west, and mud diapirs in the east. So these are some physiographic features that everybody knows about. All right. Now, paleogeographic reconstruction, and then you have seen these models, the section models before, these ones here. But here is the paleogeographic reconstruction of the subduction complex. Aptian meaning middle of Cretaceous, and Danian meaning early Paleocene. And as you can see, India, the Aptian is in the mid Cretaceous, is still way down here. It started moving very, very rapidly after that before it collided with Eurasia. And here is in the Danian, you can see it has moved very rapidly, and it's already here in the Paleogene. And so these are the Berg's models, which we have seen before, going from the mid-Cretaceous shows a spreading ridge, as well as the subduction accompanying magmatism between Arabia and Eurasian plates. India is still attached to Madagascar. The early Paleocene reconstruction shows convergence in Neotethys and subduction between Arabia and Eurasia. India is now rapidly moving northwards, and the cross-section shows single seismic zone in the early Cretaceous with magmatism changing to double seismic zones in subduction zone in the late Cretaceous and Paleogene. So, and I will show you tomographic images where you will be able to actually see these old parts of these plates, these bits of these old plates that are now subducted. You will see them in the deeper lithosphere. Here now cross sections below here shows subduction zone persists until the subduction zone persists until the early Eocene, changing to a single one here. Already here in the late Eocene, and by early Miocene, it looks very much like the present day. Now here is a reconstruction of the provenance of sediments. Where was it coming from? So when you compare the sediments that have been recovered from the ocean, you look at the provenance, you see that they are they were derived from all of this area, and because of the uplift of the Zagros Mountains right here. There are two cross sections from the east and the west that are now here is a and B, as you can see, and these are the east is at the top now, and the west is at the bottom, and you can see here Dia has attempted to correlate the land to basin parts of the east and west. Macron is younging, of course, oceanward. Is this way, ocean is this way, so it's younging this way, and becoming older and older this way. So Eocene into Pliocene, Pleistocene sediments have been mapped and represent a synthesis of previous works as well as our new interpretation based on seismic data. Here is another seismic interpretation across eastern Macron now, and as you can see, I had to cover up the seismic lines, but you can see the interpretations here very nicely. A and B are seismic lines across Macron accretionary prism. A map means Macron accretionary prism, abyssal plain, Little Murray Ridge, and the abyssal plain itself. Notice that the imbricate thrusts comprise Little Murray Ridge. So Little Murray Ridge is right here. This is the Little Murray Ridge. So it is a little higher than the rest of it, but it also comprises of this imbricate thrusts. And C and D, you can see the line and the interpretation that goes through Dalrymple trough. This is the more shallow compared to this raised area, which is the Indus margin, and then the Murray Ridge here. So this is just to show you the structure of the surrounding. Notice the mass transport deposit along steep margins of the fault. So these steep margins have these mass transport deposits. These are chaotic complex of sediments that are derived from uptip because of steep margins. And here is the easternmost Macron seismic sections and interpretations. You can see that this is the seismic section itself, and then synkinematic strata, so that actually tell us which strata were were being laid down while deformation was taking place. That's why they're called synkinematic, and the stratigraphic ages of those. And you can see that late Miocene is predominant in here, but there is also some early Miocene and some Oligocene, and below that some Eocene as well. So there is very little well data in this area. So a lot of these age models are based on cross correlations from distant areas. So this is one of the main disadvantage of studying this area, is because although there is good seismic data, there is not enough well data to actually be absolutely certain about the ages of these. So these are probably pretty close, but they are not. You can't be absolutely certain that these ages are absolutely what it says here in this legend. So you have to take that with a pinch of salt. So age module is available on a paleo data in wells and cross correlations. Okay, and now here we have another line from central Macron, the seismic line. In this case, I can show that because you can't see much of the seismics anymore. It's just the interpreted part, and you can see again seismic interpretation, synkinematic strata interpretation, and seismic, which also shows the seismic facies, and as well as the stratigraphic age data here. So typical imbricate part of the margin. This time from the central part of Macron, accretion very closely spaced imbricate thrusts and syntectonic strata deposited during deformation, and age model again based on little data that we have. on there. And then here is the seismic interpretation for the westernmost part of Macron, and they're now on the Iranian side. And as you can see, the synkinematic strata again shows a lot of deformation of the sediment as they are being deposited. Here are the mini basins on top of these wedges, and the thrust faults. And here are the ages of those Miocene and early Miocene and late Miocene and Oligo-Eocene in the bottom. Okay, so I'll quickly go through that. Now, where is the sediment coming from? Sediment input pathways, and this is very important. If we are going to go for the oil in this area, then we have to know where the sediment is coming from, what is the nature of the sediment, whether any of it was organic rich, and all of those things. And for that, you need to know the provenance of these sediments. And here is a very good synthesis of the provenance. This is all new data. It has never been seen before. Inferred from the seismic data, this shows the sediment flows pathway onshore to offshore. Thick Pliocene pile of sediment here in the Zagros Mountains, because the Zagros are still, they were rising rapidly in the Pleistocene, and that means that the relief was being enhanced constantly, and that produces this thick pile of offshore sediments in this area. High Oman input along Oman margins. Oman has also, in the abyssal plain especially, a lot of sediments come from this side as well as from that side, and they're mixing together. Okay, sediment dispersal pathways. Dia has made some models here at different times. Here is the early Miocene, here is the late Miocene, and here is the Pleistocene. And as you can see, in early Miocene, major dispersal is via the Katawaz Delta. Katawaz Delta is up here. Indus Delta is down here. But this is Katawaz. This is the old Delta, pre-Indus Delta. And a lot of the sediment was coming through here at that time into the Macron accretionary prism and abyssal plain. It's a proto-delta, and it was a minor delta. But it's important in the early Miocene. By late Miocene, Indus dispersal system becomes more important. So Katawaz is no longer important, as important, but Indus becomes more important. On Macron, north to south, dispersal is now established. So this is also north to south dispersal is also now possible. Although it's not a major source of sediment, it is certainly because of the continuous uplift of this margin. With every major earthquake, you are making relief, and that relief provides a lot of the sediment in the trench. In Pliocene, these dispersal patterns continue. Okay, now here is a very nice bathymetry. Picture of the bathymetry. The German researchers have taken these these very nice bathymetric pictures of with their system on their ship, and you can see a lot of deep canyons are seen here on the Pakistani Macron side, but not so deep and not so prominent on the Irani side, and that's also a very distinct difference. And here, so high resolution bathymetry shows several deep canyons and tributaries in the east, and less pronounced canyons in the west. Lower figure shows a model of the size of present-day sediment catchment areas along coastal Macron. As you can see, the catchment area on the east becomes and the west, the catchment areas are about 4,000, little more than 4,000 square kilometers, and here in the west, in the east, it becomes more. They can become much bigger, 31,000 square kilometers in the east, and this is related, of course, to the wedge size area size. Sorry, this is also the case in Pleistocene. fluvial input in the first order control on sediment piles along the Macron accretionary wedge. So river sediments are very, very important in this area. They have been brought in to this area. And now, summary of conclusion. Before we go to tomography, I want you to just look quickly at this the summary of that we have so far. Macron accretionary prism displays two distinct morphotectonic regime, an imbricate fan and wedge top basins towards the coast. Deformation of the wedge top basins depends on sediment rate across the wedge, which in turn is dependent on the size of catchment area's uptip. Westernmost Macron shows thick Pleistocene accumulation source from the Zagros range and their continuous uplift, and mud content increases east to west, culminating in thick mobile shales in the westernmost Macron, where progradation of Macron wedge competes with the northern Oman gravity spreading system deformation, resulting in local mini basins in that area. Okay. Now let's look at tomography area in this second part of the talk. Here is the Alpine Himalayan range again, and here is the two pictures of tomography, one at shallower depth of 400 meters, and the other one at 1,000 kilometers, sorry, not meter, kilometers, 400 kilometer depth, and here is 1,000 kilometer depth. And the hot areas are red and the cold areas are blue. And of course, the subducting slabs are going to be cold. They are cold oceanic crust, and therefore they will be blue. And now, what is seismic tomography? Just a small introduction. In seismic tomography, P and S and surface waves produced by explosions, artificial explosions by dynamite or earthquakes. Even earthquakes can help us produce good tomographic images. They are used to construct 3D models of velocity anomalies of the moving waves that can be interpreted as structural, thermal, or compositional variations. Okay, so tomography these are especially useful to study deeper core, mantle, and plate tectonic processes. This figure shows the tomographic velocity or thermal anomaly at 1,400 kilometers in the Alpine Himalayan areas. And as you can see in the Macron area here, you see some of these blue areas. That's the subducting plate, prominent at 400 kilometers, but not so prominent at the 1,000 kilometers depth. So, but I'll show you some more. The colder blue subducting slabs mark the location of Macron subduction zone, clearly seen in 400 meter depth, but subdued in the 1,000 kilometer. Okay, now here are some cross section. They run from north to south, and as you can see here, they are actually mostly from west. They're all from western Macron, and they run into northern Iran. So this is the Macron area, and that's run into northern Iran. So you can see that in here in this picture, but much better. And as you can see, these blue slabs represent old, colder slabs, or these are what we call graveyards of old slabs, subducting slabs. Here is the present day slab, and then you can see that there is an older bit of this slab underneath the warmer crust above. And you can also see further deep older parts of the slab as well. So again, you can see in these models, especially in H, right here, this has been modeled, and there is consistent. The red means that all the models show consistent velocity anomaly in this area and this depth and this depth. And the red doesn't mean hot here; it means that higher number of certainty, higher number of certainties. That slab was here and slab was here at some time in the past. So all of you can see the cold Macron slab subducting underneath the warmer Iranian lithosphere. It shows the warmer colors with the slabs where images of the slab agree most, and I shows the cross section that was imaged. Okay. Here we have now a strike cross section. You can see that it runs east-west here. The other one was north-south. And as you can see that here also, you can see bits of the old Indian slabs that were actually produced by the moving Indian plate when it was subducting underneath the Indian, the Eurasian crust. And here is the bits of the Indians. Here is Arabia, here is India, and then of course there are the Zagros also has its own slab, and the Afghanistan has its own slab underneath. So these are all slabs that are buried underneath these continental lithospheres, which were active at another time. That's how we know that there were old subduction zones here, fossil subduction zones that are no longer visible to us because they're all being subducted down below the continental lithosphere. Okay. This is why geoscientists have constructed history of subduction in the Oman Macron region as that of multiple subduction zones as evidenced by multiple slabs. Now these are a couple of dip sections, more pertinent to Macron itself, and as you can see that they are from different central Macron, eastern Macron, and then western Macron. These two of them, and you can see that the plate, subducting plate here in blue, and an old bit of the plate, and then in between there is an interruption in subduction. So the subduction was definitely interrupted for a while in this time. As you can see this more clearly here, that slab is down here, up here, but in between it's absent. So that gap in subduction is an important tectonic clue for us. And as you can see in the central Macron, it's a more persistent slab going down, and of course in the easternmost Macron, it becomes a little bit less prominent than the rest of it. Okay, so all of this I've already said. And now here is another dip section, this time in the Pakistan and Afghanistan ranges. And as you can see here also, you can see the slabs, older slab and this current slab, but with the older parts up here. Again, two bits of slabs under Suleiman range that are old slabs that are now buried, completely buried. And then here in the Hindu Kush, with Western Hindu Kush, you have a slab, and then Eastern Hindu Kush, you also have old slabs. So these are all evidence of location of these tomographic depths is not along the coast, but further through north through Iran, Balochistan, and Afghanistan, covering Kithar, Suleiman, and Western and Eastern Hindu Kush. So you can see these cold bits of the slab. This indicates that the history of the region has been much more complex than we have known before. The textbooks have to be rewritten because of this new evidence. Okay, I think since my time is coming to an end very soon, I better hurry up a little bit. So here is another depth slab. Again, I wanted to show you that that the evidence is consistent. Here is the transition zone. This is the upper mantle. This is 110, 240, and 500 kilometers. As you go deeper, it becomes less and less prominent. In fact, cold parts of the slabs essentially disappear at 500 kilometers, but they're still prominent in 240 kilometers. That is the upper mantle. And also in the lower part of the lithosphere, they are still prominent. This one right here. Okay, so I've already said all of that. Now here is a nice sketch that Dia has made based on all the information that he's gathered from the tomographic images, and you have seen some of these lines already. Here is the Macron looking southwards. Here we are sitting, we are looking at it from the northeast, southward, southwest view, and the Zagros mountains are up here, and the Kirthar Suleiman range are up here, and here is the Chaman Fault, which is the boundary between the Indian plate and the Eurasian plate. And as you can see, there the slab not only is dipping northwards, but it's also tilting north westwards, and even steeper further in Iran. It dips even further steeper. So there is a tear in this slab right here, and so it's a complicated history that is been unraveled for the first time. This is an attempt to understand 3D structure of the Macron subducting slab. Macron coast and Zagros are at the top, and as you can see, the slab is in several bits. Okay, there is also the remnant of an older Indian slab, but bit attached to the so this is probably the old Indian slab, which is now attached to the younger Macron slab. Here is the same picture again, a little more in color. You can see that here is the Macron and Kirthar Suleiman range, and Zagros is right here. The range is right here, and this is another view from the same direction, and also the input sediment input. Okay, so and of course this is all based on mapping the slab boundaries with the help of tomography at their depth and their widths, as well as from all those images. And you can see that there are several bits of these things that have been mapped. The tomographic data allows us to trace the extent of the current slab and the older slab underneath Iran, Pakistan, and Afghanistan. And of course, here is a tomographic image of the of the hemisphere at different. This is 200 kilometers, 400 kilometers, and 600 kilometers. The reason you can get good tomographic data is because of the earthquakes. The earthquakes generate a lot of good tomographic images. They are strong. They are stronger than any explosions we can use artificially in the ocean, for example, to get images, or on land to get 3D seismic. So we are limited to less powerful, producing less powerful waves, and therefore we have to depend on the earthquakes to do the job. So many of these tomographic images have been created by mapping by the help of earthquakes, this is just to show you that the data comes from a global set of data. Worldwide tomographic data now allows geophysicists to image and understand the depth structure of the mantle and overlying crust. Below 200 kilometers, the lithosphere mantle is quite hot. But above that, of course, the subduction plate. And here is a model reconstruction of the subducting slab in the Eocene, Oligocene, and Neogene, as they may have looked. This is just a model. So, how good it is, anybody knows, because the parameters is mostly based on taking the old slab and then moving them back stripping them into their earlier positions, assuming a constant speed, which may not be the right thing to do. So anyway, these are good attempts to understand what these things might be doing in the past. Okay. Now, at the end of this study, Dia has produced a very nice synthesis map, an updated synthesis map of the Macron region and north, for the north, in the study area, and of course, of both Pakistan and Iran. And he has he's put all the offshore and onshore data together, and has made a new map, which is much more detailed with a lot more information. And this, of course, will be published and will be available soon. And of course, now we come to the summary of conclusions. Prior to Eocene, the eastern and western Macron shows stark differences. West Macron was more akin to Arabian Neotethys with blue schist exhumation, and East Macron was akin to Indian Neotethys, continental and oceanic arc associated with the subduction zone. The Macron-Quaternary prism has evolved as a single geodynamical entity since the Eocene. After the Eocene, it became one unit with near field processes dominating. What are the near field processes? These are the local slab dynamics that are more dominant for Macron from Eocene onwards. Oligocene and Middle Miocene is marked by the growth of a Quaternary wedge with the clastic source from the surrounding higher relief. This is also a period of transition from dominantly slab dynamics to an advancing trench at the subduction zone, as well as far field influences due to the collision of Zagros in the west. Late Miocene is marked by deformation of the whole Macron-Quaternary prism and deposition of a major olistostorm or slump deposit, mass transport deposit, as I mentioned earlier, in western Macron as a result of the slab tearing in the west. Pleioplasticine saw further isolation of the wedge, greater influence of both far and near field influences with ongoing Zagros and Kirthar collisions, as well as extensive reworking of the wedge. So this is the total history of the Macron. And while Western Macron shows large wavelength fold and fault structures, Eastern Macron deformation is mainly tilted strata towards the coast. The Central Macron shows imbricated thrust with short fold and thrust spacings. Okay, so these are the main conclusion. And now what remains to be studied? Of course, there's a lot remain to be studied. By no means we know everything here. In fact, we've just skimmed the top. Detailed analysis of Macron-Quaternary prism sedimentary evolution can easily be carried out with existing seismic data. Some of it after reprocessing, especially for the deeper sections, which we haven't done yet. This work was limited to pseudo 3D study of the tomographic data based on 2D data, but by doing a normal 3D study of this data, pre-deformation slab structures can be much better documented and reconstructed. The Macron subduction zone and its accretionary prism is a unique laboratory where subduction dynamics and far field influence can be demonstrated. Lessons learned here could be used for other living and fossil subduction zones around the world. So Macron is a very good example of subduction zone, and I think in future you will see much more interest, both international and also from Pakistan in this area. And also I think oil industry is going to become interested in this area again. In fact, they already are interested in this area. We know that. Thank you very much.
Thank you very much, Dr. Bilal. It was very thought-provoking lecture. And at present, we have two parts for question. One is from audience. Almost 125 students are present in the hall along with their teachers. First of all, I request you, if you have any question, please raise your hand. Then you will come to the dais and ask question to Dr. Bilal. Please. Yes. Come here.
Assalamu alaikum, sir. I'm Ahmed from Somalia. Sir, I would like to ask you what relationship between geological relationship between Somalia and Pakistan. The second question is what role Somalia is playing in the region in terms of hydrocarbon and plate tectonic. Thank you, sir.
Okay, all right. That's a very big question. Somalia is quite far from Oman, so we only studied northern Oman, bit of the northern Oman, and so it was not a part of the study. Unfortunately, I know a little bit about Somalia, but I'm not to answer your question.
And any other question? Yes, Dr. Saifur Rahman.
Sir, what you have concluded about the delivery of fan system in the Macron area? Either it was deposited by a single system or deposited in a multi-system. One of our industry person, Mother Keyu, proposed it was deposited in a single stage, a single system. So what do you have concluded in your research? Thank you.
Actually, you remember the pathways of sediments slide, which clearly shows that sediment came from lots of different places. And, it's not a single system. Macron is a very big area, and the sediments coming from near shore. Macron itself, also from distant, the Oman Crystal Plain sediment is largely from Oman side, and the Iranian Macron sediment is mostly from Sistan and rivers in the Sistan area, and also from the Zagros ranges. Whereas here we are getting sediment from the Qatar delta, the ancient delta, pre-Indus delta, and later on we are also getting some input from Indus delta. But the source largely is from the multi-source stadium, not a single source.
Yes. There is another question from a student, Bushra.
Assalamu alaikum, Dr. Bilal Ul Haq. I want to ask you what is the importance of this area and the proven petroleum system of this area?
Well, there are lots of problems with this area when it comes to petroleum, because it's an active margin, which means tectonically active today. So a lot of the old sediments have been subducted offshore, and onshore you may find some, because there are lots of good porous sediments onshore. There's a lot of work that was done on sedimentology in the 1970s and 80s. American companies, and they are published, and everybody is aware of them. The problem here, of course, is the source. No, it's not the reservoir, it's the source problem. And of course, also maturation, whether you can have it buried it long enough that you can mature. But in these kinds of systems, oil has been found, like Northern California and Central California, that's overriding the subduction zone as well. And there you can see that there is oil there. So we can't give up. We just have to understand it a lot better than we have before we can say something about the petroleum system.
Thank you very much. Another question from Ahmed Raza. He is doing PhD in China. Please.
Assalamualaikum, sir. Sir, I want to ask you about the large mud volcanoes in Macron zone. As some workers suggested that the Macron not only grew by the accreting sediments at the wedge, but there is also some underplating process may be called decolement, which are the weak horizons. So what are the relationship between these decolements and the large mud volcanoes in the Macron zone?
Well, the mud volcanoes are quite common on subduction zones. It's because you are squeezing out a lot of the methane, and when you're subducting, you're under pressure. Further in the back arc, you are producing volcanism, but closer to the trend, you are producing a lot of volcanoes. Mud volcanoes are common. In the Macron, the mud volcanoes are very good. They are very good examples. They're all exposed on land, but lots of these mud volcanoes are actually submarine. They are found underwater, and we also have on seismic lines. We have seen many of them on Macron as well, both on the Pakistani side and on Iran. So this is a common phenomenon of subduction, where you are squeezing out methane from older sediments, and then the methane comes out into the mud volcano.
Another question is Saad. He is student of final profession.
Well, hello, Assalamualaikum, sir. Thank you for such a great talk. My question will be that you see the Macron area is really complex, and the whole subjected area. How do you see the exploration for the petroleum there? You know, the whole system is really complex for the exploration to be carried out. So how do you see the most efficient way for the petroleum geologists for the exploration there? Thank you.
Well, the easiest way to do it is to take all the existing data and synthesize that. And I think that is something that can be done very easily. For that, you don't have to go offshore. You actually can stay onshore and study the onshore data. In detail. I think before you can do any more 3D seismic surveys, which will probably become necessary once you've identified an area that looks promising from its the various structures and reservoir and source rocks availability, then you can do a 3D seismic survey, and then you can pinpoint the more promising areas on the basis of that. But this is all something that the petroleum scientists in Pakistan know about. I have met many really very experienced petroleum geologists in Pakistan. They're world class. They know what they're doing. It's just that their attention hasn't been drawn, except maybe PPL. I don't think anybody else has really the Macron area. I think we have to convince them to go there and spend some money exploring.
Last question from the audience, then we will go to the international audience. So, Dr. Jawad, please.
Assalamualaikum, sir. Sir, I would like to question about the sedimentary fishes. You are talking about sedimentary fishes. You have interpreted this data from seismic only, or you have used some core data?
Yeah, well, there is some core data in this area. Paleo data is limited, but I think seismological data on the Irani side especially is quite common and well established. On the Pakistani side, we have several wells that the industry has, and there were also some legacy data from old, onshore as well. That Marathon Oil one time was very interested in that. In fact, they were the one who convinced me that this would be a good PhD project for a student, and that's how my student got involved in that marathon data. And so there is some well data, but it is largely the cross correlation, long distance correlations are all based on seismics.
Now we will invite to questions from international audience, industry people, and academia which are not present here. So, Dr. Arvind, who is first?
Okay, Dr. Ghosh, it's your turn right now. You can ask the question of Bilal Ul Haq. Yes, okay, Dr. Ghosh.
Next level.
Next question is from Smart. If you have a question, you ask Dr. Bilal, he is there to reply you back. Answer Smart. From the
Can you guys hear me?
Yes, yes.
Sir, first of all, I would like to say that it's a big presentation. My concern is that we have our client in the area, and that we feel that with respect to drilling, there are large problems with respect.
Excuse me, I hear an echo. So I can't hear the question clearly.
Answer Usman, please turn off your mic, speaker, so that you can hear.
Yeah, I hear an echo.
The same problem is with me. There is some sound of.
Answer, please switch off your mic, switch off your speaker. Switch off your speaker.
Okay, sir, please ask your question now.
Okay. Can you guys hear me now?
Yes, it's fine.
Okay, sir, my concern is that we have worked for our client in the area, and what we observe with respect to drilling is that there are huge problems, especially with respect to the pore pressure, and the main concern is that the deposition in the area is very high in some of the regions. Can this study provide any help to identify the areas which have high deposition rate and are prone to more pore pressures and overpressure areas?
Okay. All right, can you hear me now? Can you hear me? Can you hear me?
Yes.
Okay. No, this study will not give you that kind of information because that was not the it was that is not that kind of a detailed study, and it's more a tectonics are the sedimentary so far. So of course there is intention to go and do much more details of the existing data. But we don't have that kind of information at this point.
And another question is from Professor Subarta Ghosh. Professor, please turn on your mic first. We cannot hear you.
Okay.
Yes, your mic is not. Mic is on. Please ask your question. I'm sorry, Professor Ghosh, the time is up now. Please send us your question on email. We will try to send you answers. So the time for the Professor Bilal Ul Haq talk is over now. Now we will move to the next talk.
Doctor, thank you very much. Thank you very much for your thought-provoking talk, and I hope we will see you in Lahore next time, and then we will have you in our institute for another lecture. Thank you very much, sir.
Okay, our next talk is from Professor Liu Keyu. Professor Liu Keyu is a Chinese-Australian geoscientist, a professor at China University of Petroleum, East China. He was recruited as a 1,000 talent expert in the research of petroleum exploration and development, and as chief geologist at Petroleum Geoscience Research Center and Laboratory. Professor Liu Keyu worked in various organizations in Australia for over 20 years, including Commonwealth Scientific and Industrial Research Organization, Adelaide University, and James Cook University. Professor Liu Keyu has published his work extensively in reputed international journals. He is currently editor of Asian Journal of Earth Sciences and Australian Journal of Earth Sciences. He is active member of AAPG and SPE. Professor Liu Keyu's main research interest includes clastic sedimentology, quantitative petroleum system analysis, laboratory investigation of oil migration, and enhanced oil recovery. I will turn on his mic, and I would request him to start his talk. Professor Liu Keyu.
Thank you. Thanks, Manama. It's a great pleasure. Can you hear me? Can you guys hear me?
Yes, we can hear you.
Yes. Okay. I will share my screen. Can you see my screen?
Yes, we can see your slides.
Okay, thank you. Thanks. To save the, I may switch on my video to save the bandwidth. Just switch off my video. So I'll leave my audio on.
Professor, please share a window, not the whole screen.
Okay, right. Okay, is that okay?
Not yet. We cannot see your slides.
Okay. Thank you for the invitation. It's a great pleasure and a privilege to give a talk today here in this marine geoscience and quaternary geology. Yeah. So the title of my talk today is the geomorphic evolution and also the sedimentology of the northern plateau, the Quaternary, mainly focused on the tectonic and the climatic control. In this talk,
Professor, we cannot see your slides.
You can't see my slides?
Yes, it is not displayed, not shared yet.
Is that okay?
Yes, now it's okay.
It's okay. Okay, thank you. Thanks. I start again. Apologize for this inconvenience. Yeah, good afternoon again. Good morning your time. So my name is Kevin Liu. It's from China University of Petroleum. So the talk today I'm going to give is the geomorphologic evolution of the northern Tibetan plateau during the Quaternary. I will mainly focus on the tectonic and climate coupling effect using landscape modeling technique to study this region. Professor Haq gave an excellent talk just before me, so I hope my talk will give you some insight for your work in Pakistan and other places. First of all, I would like to just to acknowledge a few people. Okay, this is actually the work from my PhD student, Liu. So the work is being published in the International Journal of Interpretation. I would also like to thank my former colleagues and also a lecturer from Sydney University, Dr. Tristan Salish, who actually introduced us to this Bedland computer program. He actually designed the whole program, and it's now an open source software that anyone can get access to it. So also funding from China Academy of Sciences and also the National Natural Science Foundation of China. So in this talk, I will just divide into 5 parts. I will first talk about the background of my research area. So everyone knows that the Qinghai or Tibetan Plateau is probably currently the largest and the highest plateau in the world. Okay, also with the thickest crust of 70 kilometers. It's often referred to as the roof of the world, as you can see from this image. So from here, we know it's a very thick crust, and also the Mount Everest is right in this region. So we all know that it's the geodynamic moment in this area, actually probably the most important global geoscience event in the Cenozoic from the Indian plate collide with the Eurasia plate. Also, because this collision and also the geodynamic setting, it has a profound impact on the climate and environmental changes in Asia or the entire northern hemisphere. We know the monsoon and the trade wind in the Asian countries, it's partly because of the uplift of the Tibetan Plateau and also the mountains within it. So the basin I'm going to talk about today is the Chedam Basin right here in the northern Tibetan Plateau. It's a intramountain basins or intermountain basins. So at an elevation of around 2,600 meters to 3,000 meters. So the reason we choose this basin to model is because it is an enclosed basin. So all the sediment from the surrounding basin dump into the basin, and we can really work out the mass balance. We know how much sediment gets in. It always has been preserved within the basin. So this is one of the reasons we choose to model the Chedam Basin in the northern Tibetan Plateau. So first, it's in the northern part of Tibetan Plateau, right in this area. The size of the basin is around 120,000 square kilometers. It's quite high, as I mentioned, that's around 3,000 meters above sea level. There are mountain ranges surrounding this basin, including to the west, the Altai Mountains, to the north, the Chilean Mountains, and to the south is the Eastern Quaternary Mountains. So it's all surrounded by these high-rise mountains in this area. So we're going to do a tectonic evolution of the Quaternary based on numerical modeling. So here are some shots from the Chedam Basin. You see the landscape, it's a rugged terrain, and also there are lots of planation surfaces, river terraces that can be used for dating the uplift of the plateau and also the surrounding mountains. So we know it's the largest Cenozoic terrestrial intermountain basin in the world at the moment. So it is really ideal for understand the mass balance of sediment source sink study in this region. Also, it's good for studying the coupling between tectonics and the climate interaction for sediment evolution. Because we know a very intimate relationship between climate and tectonic in this region, and it affects the whole entire Asian climate and also perhaps the northern hemisphere. So there are lots of studies in this region. We know particularly on the sediment evolution or structural process, but among all these studies, sometimes they only focus on particularly a section, like a Western Chilean Basin, or so eastern part or northern part. They never been a comprehensive study of the entire basin. The other issues in this previous studies is most work has been qualitative and conceptual. So in the other studies, we want to study the entire basin as an entity from the viewpoint from a source sink and also from a quantitative approach. We want to know how much sediment contribution from each sector and what the impact of climate or tectonics on the sedimentation and also the basin evolution. So just to give a background, there are currently two viewpoints on the Chunghai Tibetan Plateau, the uplift timing. One group believes that the area has been attained to its present height in the middle Miocene or even earlier. So this is primarily based on isotope geochronology, also published geochronology and the plant fossils. So this is a viewpoint held by one group of people, such as Clark in his 2010 paper, and a few other peoples, and Spencer 2003. So so this is one group of people's view. But on the other hand, the second group of people, again, this Clark 2010 and also one 2017, they believe the plateau only reached its present height in the Quaternary. So we want to test this a controversy. When did the plateau reach its current height? So this group view based on a number of megafaunas like rhinos, elephant, giraffe faunas found dated in this region. So they believe the climate setting during even 10,000 around certain regions is still livable for big animals. So they believe the uplift of the entire area is quite late. So this of the scenario we want to test in our simulation. So this I'm short of the big faunas found in this region. We're talking about megafaunas. So the key issues we want to address in our study is include, we basically want to build or construct a tectonic evolution model for the entire basin. We call it 120,000 square kilometers. We want to check the timing of the uplift because there are controversies at the moment. So one group is saying it's very early, the other think it's in the Quaternary. Thirdly, we want to understand the factor that's controlling sedimentation, whether it's a tectonic zone or climate or the coupling of both control the sedimentation within the basin. Finally, not least, we want to understand and quantify the source to sink in this region, because as I mentioned, that it's an enclosed basin. It's got sediment supply from 3 mountains ranges. So you want to understand what the sediment contribution from each range. So I'm going to talk about the method, spend some time on the method. So I think this biobedland is basically it's short for basin and landscape dynamics. Okay, so I use the red for PY essentially is a Python algorithm based, computing language based. It's a Python based open source and parallel computing landscape modeling in a program that can simulate both erosion and deposition. This is actually the program created by one of my former colleagues called Tristan Salish that can be used to investigate drainage evolution over in a continental scale up to hundreds of millions of years. And it can also be used for a small scale, short-term landscape evolution. I'm going to show you quite a few examples. So essentially, so the program can simulate the landscape uplifting, denudation, and deposition by considering a number of factors and processes, including hill slope using simple creep law, overland flows for stream power using stream power law, and the flux aesthetic, the tectonic loading, and also the sediment compaction. So in this program we used for the simulation, basically contain a number of terms, like including the continuity of mass, the erosive power of the water flow, diffusion process, and tectonic. So this is essentially the key equation within the bedland program that we use. So this is the author of the program is my former colleagues from CSIRO and now in Sydney University, Tristan Salish. So he has created this program, and currently it's open source, being widely used by many people in different parts of the world, including my students. And actually, lately, someone from University of UT Austin just published one paper in geology using bedland to simulate for simulation. So this program, by simulate the landscape evolution and sedimentation, so we can we can do a number of things using the following example to show you. Okay, first, for this program to use, we need to use the online the Jupyter environment. So it's script based. It's on the internet. We can access to the open source network, open source code. The Jupyter notebook basically also an open source web-based application, so which allow you to create a shared document that contain live code, equations, visualization, and narrative text, include data transformation, numerical simulation, modeling, data manipulation and visualization, and even machine learning, and much more. So it's an excellent open source environment. We use this often in our research. So in this environment, we can start the bedland program, which is also an open source program, and set up our model and running the program. So when we run the program, it has some general structures. It's based on the XML input file format. So we can set up the program by setting the grade, time, strata, sea level, tectonics, precipitation, surface process, erodibility, hill slope process, waves, if we do a marine setting, and carbonate modeling, fracture aesthetic, and then output. So this is actually the structure of this model. So, for example, just for the grid structure, it's everything is working in a grid. You can use XYZ data to input. The low left corner to the upper corner, this is north to the upper is north. So we can set up all our input profile based on this format, this grid format. So this workflow, we can set up our program using discrete input, such like tectonic topography, sea levels, dynamic topography, and also on the other hand, we can also do some statistical distribution on the initial topography, erodibility coefficient, and precipitation. We can do a continental scale landscape evolution model, or you do a local scale modeling. But for all this work, we need to do a model validation using present-day topography. As in our case, we use the Google Earth derived DM model, or counter rivers and sediment thickness. So we have to validate our model before we accept as the final reasonable model. Okay. Well, once we set up model, then we need to do the simulation, or we call processing. In one part, we call the morphometric processing. Basically refer to quantitative description analysis of the produced bedland surfaces, which can be used for a particular kind of landscape, or to a drainage basin and a larger region. So in this geomorphic attribute can be extracted, including the gradient, so the magnitude of maximum gradient, horizontal curvature, vertical curvature, aspect, this basic direct maximum gradient, and discharge. So we can get all this information from the model once we complete it. So this is the morphometric analysis using in the bedland simulation. We can see this precipitation and also the orogenic precipitation with time. So this is the process in this model. Okay, just to take example, this one we using the stratigraphic analysis. Once now this options turned on, the bedland can try to produce a landscape and also sediment deposition. And in this one, we have this one. It's the dark brown is sedimentation, and the blue part is denudation. Okay, we can see this. This is running 30 million years deposition. You can see this sea level up and down, and also interact with the drainage, sediment erosion, and deposition. This work has been done by a student with the Tristan Selish in Sydney University. Once we done this, we can do a cross section to analyze this quantitatively of the stratigraphy. All this is done using peer review within also open source code. We use this to realize the program and the simulation result. So for the stratigraphic record, it not only can do the space domain, also can do a time domain, doing the Wheeler diagram in 3D. So we can build the landscape and stratigraphic record in space domain, and also in the time domain in 3D. So this is quite useful, as quite often we need to know the sedimentation rate, the deposition and denudation, and the mission section in a basin sequence. So this is quite useful for quantitative analysis like basin modeling. We need to work out exactly how much sediment has been denuded or missing at a certain unconformity. So this is an excellent program for us to use. Also, it can be used to reproduce the discharge of landscape. This is southeastern part of Australia, and also the catchment characteristics to complete the source-to-sink analysis of sediment. That's why we use this for the Chatham Basin to basically quantify the source-to-sink, the sediment contribution from particular part of the basin, and also to ground truth the exhumation history, and also it can be applied to lots of other places as well. So this is another example. We use it to model the Australian continental margin, highland formation. In one of these, the model is capable of simulating what we call the hill slope process, like using diffusion law, the fluvial erosion using stream power law, sediment transport using sediment flux conservation and deposition in a depression area, as well as acidic fracture and heterogeneous lithosphere. So this can be all modeled within this program. So it can be used to quantify the geomorphic and central response to spatial and temporal varying tectonic and climate force, particularly with the precipitation at sea level. So this is the part that we use in the Chatham Basin simulation. So we really want to understand the geomorphic and central response to the uplift of Tibetan Plateau and to the glaciation and interglaciation in the region. So this example using Badland for regional scale model, again in the Southern Australia, we can see this very short period from only 40,000 years. So you can see the change of the shoreline and the denudation patterns for this region. However, this is a better example. This is a very short-term simulation. We're talking about from 2020 to 2,500. It's only 480 years change. This is the northern New South Wales in the eastern coast of Australia. We call it the Tweed Head. It's just near the border between New South Wales and Queensland. It's a summer resort town. There are lots of huge people living there, but the area is subject to coastline erosion. So by doing this, we can inform the government or the people that the land with a certain sea level rise, what's going to happen with your coastline and also the living area. This is a large-scale simulation of the almost entire Australia. You can see this. We're talking about 100 million years and 1,000 kilometers landscape. So basically, this project started by Tristan Selish in Sydney. We try to model sea level changes and also the deep earth mantle convection, coastline evolution, erosion of sedimentation, the river network evolution, also the erodibility and rainfall. So this we are talking about millions of years and also 1,000 kilometers across, involve the deep earth process and surface process. So the coupling between the climate, tectonics, and also sea level changes. So you can see this, the drainage pattern changes. This over hundreds of million years. So this program can be powerful for doing the work we need to address our issues. Also, it can be used to do modeling of barrier reefs, coral reefs growth. We're talking about only 10,000 years growth in the Holocene or in the late Quaternary. see the shoreline changes and the Australia Great Barrier Reef in the northeastern Australia. We can see these changes using this program by influence sea level and the growth of the coral reef and the sedimentation within it. Also, we talk about the sloping process. These are the slide into the basin from the steep slope. So currently, this program has been coupled with the geoplate and other programs to do evaluate the deep Earth process. We talk about the tectonic and mantle conversion on the basin evolution. So by combining G-plate and other sitcom and this simulated dynamic topography, we can coupling the bedland during the initial to simulate the topographic evolution, erodibility, precipitation, and sea level. Using this process, we can just link the surface process to deep process. So this is the workflow. Actually, from G-plate, sitcom, we get the large-scale dynamic topography of the continent. Then by using incorporate with bedland simulation, we can simulate the precipitation, paleotopography, sediment thickness, the polar environment, and also we talk about denudation rate and sea level changes. So all this you can, if you are interested in, there is a link here. This is the Earthbite group in Sydney University with Dieter Müller as the group leader, and also Tristan Selisch is the one of these lecturers in this group. So you can see lots of information within this website. Okay, www.earthbite.org. Now we can talk about our model setup. So as I mentioned before, so the Chadam Basin is in northern Tibetan Plateau. It's an area of intensive study by many peoples. But the big issue there is people most focus on a particular part doing qualitative and conceptual studies. For us, we want to study the entire basin right here. So we talk about 120,000 square kilometers basin surrounded by 3 big mountain ranges. So we want to use bedland to quantitatively simulate the denudation and deposition of the Chadam Basin and surrounding ranges. To quantify the contribution of the source to sink, because the Chadam Basin is an enclosed basin in the Quaternary, so there is no sediment out or in. So basically, all the sediment is dumped from the mountain ranges and being preserved within the basin. So this provide an ideal case study to quantify the source to sink contribution. So let's look at the Quaternary stratigraphy. The entire basin contains up to 3,000 meters Quaternary sediment. It's a lot of sediment. It's mainly mudstone and sandstone and shale with certain part of evaporite, halite. Sometimes we have some carbonaceous mudstone in there. But mainly it's lacustrine sediment. It can be a saline, lacustrine, fluvial, deltaic sediment. In this sequence, what we can see, there are 4 tectonic uplifts from roughly from 2.5 million years. We call the Qingzhang moment B. And then at around 1.7 million years, there is a tectonic uplift of the Qingzhang moment C. At roughly around 1.2 million years, there is a Qin Huang movement. And finally, at around 150,000 years, this is the Gonghe movement, the last tectonic movement. So basically in this diagram, we can see few lines. This is the dashed line here is the uplift of Tibetan plateau. Okay, so this is the marine isotope record, MRS, and this evolution. So we see the Tibetan plateau start from 1.8 kilometers all the way to the present around 3 or over 3 kilometers. For this dashed dotted line, it's the uplift of the main mountain peaks. I start from around 2.5 or 2.7 kilometers to roughly over 4,000 meters. So you can see that over the very short period of 2.5 million years, there is a significant amount of uplift in this region, in the Tibetan plateau and in the surrounding mountain ranges. So this is actually we have the magnetic age, paramagnetic age, and also these marine isotope stages from stage 2 all the way to stage 98. So this provides very good control on the timing of the uplift. Also in the diagram, you can see this is actually the glaciation. This stands for the glaciation. This is the ice age of Tibetan plateau. It starts from around 0.8 million years. We start to see ice stages in the Tibetan plateau during various stage. Okay. So this actually forms the basis of our modeling. So we know our model starts from 2.5 million years all the way to present. We want to incorporate the tectonic uplift, climate. We're using the marine isotope record using stage 1 to 98, and with the timing we're using Paleo. We also consider other information in this region. So to build the model, we need to understand the Paleo topography. So this is the cross-section from right here in the northeastern part of the Tibetan plateau. We got one profile here from Hezur to Lixia. We can see the uplift of the plateau basically is a metal plate movement and this spheric tectonic deformation, because the colliding of India plate with the Eurasian plate causing tectonic uplift and warping. So basically we need to use integrated geomorphological and paleontological evidence so to reconstruct the paleo topography or paleo geography to build our initial surface. Also, we're using data published by other people. For example, this Zhu in 2003 identified 5 tectonic uplift in this region from tectonic movement 1 to 5. Basically, it's based on the superficial analysis in a number of boreholes in this region. We know the northern Tibetan plateau basically experienced 4 features of tectonic uplift during Quaternary. Okay, as I mentioned in the early slide, the Qingdao movement B is from 2.5 to 2.28 million years. Movement C from 1.94 to 1.66 million years, while the Quinhuang movement is between 1.2 to 0.6 million years. And the last tectonic uplift is the Gonghe movement, around 150,000 to 90,000 years. So this is information we need to build into our model, conceptual model before our simulation. So obviously, based on other published information, including the the elevation of the Tibetan Plateau using this sign over from 80 million years to present. This has been well established. Also, the mountain peaks of surrounding mountains. So on that, we also build upon the high frequency climate curves using, so this is the glaciation, okay, this is elevation of the plateau, the surface, and so this is the high resolution, high frequency climate changes in this part. So we can actually correlate quite well with the 4 tectonic uplift stage from Qingdao movement B, C, and the Quinhuang movement and the Gonghe movement quite well. So for the tectonic movement, which also a parameter required for the simulation input, we actually discuss separately for different mountain ranges. This is the Altai Mountains right in the western part of the Chadhan Basin. So it's underwent rapid uplift in the early Pleistocene, as indicated by the rapid sedimentary deposition rate. So this deposition rate suggests a rapid uplift of the Altai Mountains. Also, there are seismic profile here. Also shows there are 4 feature uplift in the Altai Mountain, as I mentioned, that from 15 million years, 8 million, 3.6 million. And the last uplift in the Altai Mountain is 2.5 million years. Paleo data showing some more detailed tectonic uplift beginning around 3.6 million, and also identified the one at 2.5 million. Additionally, it's also identified the one at 1.1 million years and also 0.8 million years. So the Altai Mountain right here in the northwestern part of Chadhan Basin was uplifted and exposed after the Miocene. It was further uplifted from 2.6 to 2.1 million years and reached the present elevation in the late Pleistocene, around 250,000 years. So all this work based on the terrace, all the terraces on the Piedmont deposit and planation surface in this region. So let's go to the western Quaternary Mountain right here. So in this region, the plantation surfaces and river terraces suggest that the landscape of the eastern Quaternary Mountains, which is the southern part of Chadhan Basin, was mainly formed by the Quinhuang movement and the last Gonghe movement at 1.2 million years and 150,000 years, respectively. So it's quite late. You can see, as compared with the Altai Mountains, this uplift is quite late. So for the western mountains, we also understand the large glaciers in the beginning of the Quaternary period actually occurred in the Pleistocene around 800,000 years. So this suggests the main peak of the Quaternary Mountains must be at least 4,000 meters around 800,000 years. So the last rapid uplift for the 18 Quaternary Mountains we believe occurred at around 800,000 years, based on thermal chronological evidence in this region. There are huge amount of data in this region. Let's go to the southern Chadhan Mountain, which is the northern mountain ranges north of the Chadhan Basin, the last mountain ranges we talk about. So let's look at the snow lines. At the moment, from 450,000 years to 500,000 years. So the snow lines at around 3,500 meters. But at the present, the snow lines it's around 4,000 meters. So So from the snowline changes, we can really understand the tectonic uplift in this region. Also based on this mountain peak and plateau elevation. So we know the Chilean mountains began uplift on 3.6 million years, but later on experienced the Qingdao movement, B and C, and the Kunhuang and the Gonghe movement. So in this region, the Chilean mountain has experienced all the 4 tectonic movements in this region. So for the paleotopography, we're using the Google Earth DEM, but also at the same time we try to subtract the sediment deposit and to construct a synthetic paleo landscape based on all the studies I mentioned before. So based on hundreds of studies in this region. So we determine the uplift rate for the entire simulation from a 2.5 to 2.8. We assign tectonic uplift rate, and also for each basin, for the Quaternary mountain, Arten mountain, and the Chilean mountain. So we have this mountain range at a different uplift range based on published work. But this paleotopography is based on the DEM model. For the climate, we're using known ice age, interglacial, and glacial timing. We know the earliest Quaternary ice age in China is basically dated back to the Wangqing glaciation around 0.7 to 0.5 million years. This is the earliest known glacier in China. There are also 3 other glaciations. So basically present in the mountain ranges around the Chetan Basin, including the Middle Pliocene. There is a period of glaciation, and also the late Middle Pliocene, and the last ice age right here in the late Pliocene. So we build up all this information into our model. So this is the summary of the climate curves we used for the simulation. So here we combined the 4 classical glaciation in the Quaternary with the marine isotope stages. Okay, so it's roughly from present date all the way to around 1 million years. So we know exactly the ice age and the interglacial and glacial period. So we build in this into the R model for simulation. So for this climate, we also refer to the present rainfall in the Chetan Basin, and also assign a different rainfall for the different regions of the Quaternary mountains, the rainfall from the Arten mountains, and rainfall for the Chilean mountains. So basically, we know the current annual rainfall in Chetan Basin is quite low. It's very dry. It's only 20 millimeter to 400 millimeter per year. But the Eastern Quaternary mountains belong to a subpolar glacial zone with an annual precipitation of 500 to 1,000 millimeter. And the southern Chilean mountain is, and also the Arten mountain here belong to a polar glacier with a much lower precipitation. So there's not much precipitation here. This region and Chetan Basin also quite dry. We talking about 20 to 400 millimeters per year. So we're going to show the result here. So this is the modern area. We talk about the entire basin, 852 kilometers by 423 kilometers with a resolution of 3 kilometers. The modern duration is 2.5 million years. As you can see, we're using 250 layers display at every 10,000 years. And here you can see, I just want to draw attention, this is the Chetan Basin. You can see the uplift, rising of the mountain range and subsidence and sediment supply. This is the reddish, yellow reddish thick sediment deposition, and also the denudation. Let's run this again. I just want to draw attention to the mountain range denudation and the sediment supply basically only become pronounced at around 800,000 years. You can see this, all this in a drainage, catchment area, and sediment dumped into the basin. So this actually suggests the climate actually have a big impact on the denudation of the sediment from mountain ranges and also the sediment within the Chetan Basin. So let's have a look closely at the result. Just in a time slice from 2.4 million years also to present day. So this the elevation we can see here. This is from slice 1 is 2.4 million years. You can see this the initial evolution basically was there to main peaks around 1700 to 2500, from 2005 meters to 1700 meters. You can see this as we progress from slice 1 after the four tectonic uplift we mentioned, like the Qionzhang and the Kunhuang and also Gonghe. So the main peaks was raised to 4,000 meters and almost to there. And the basin center reached elevation of 3,000 meters at the end of Quaternary, and basically through a combined effect of tectonic uplift and substance. So this shows this profile right here. You can see the evolution of the Chetan Basin and other part. And the final geomorphic patterns, what we call this one, with evolution basically vary around 2,000 to 3,000 meters right here. So the basin has been filled by the sediment dumped from the surrounding mountains and between the mountain peaks. So let's look at the sediment. This one we talk about the topography of the Chetan Basin, and here we look at the sediment. Again, from slice 1 at 2.5 million years, we start of simulation to the final one at present day sediment. As I mentioned, this is the yellow and the reddish is the sediment thickness. So at the beginning, basically in the early Pliocene, the Altan, Quinlan, and Chilean mountains were uplifted quite violently, with most sediment supply from this Altan mountain. So after 1.5 million years, large amount of sediment was transported from the source area into the Chetan Basin over long distance, and we accumulated roughly over 1,000 meter sediment by 1.5 million years. So after the Kunhuang movement, we talk about 1.2 to 2.6 million years. The plateau reached around 3,000 meters, and glacier began to develop in the Qionghai Tibetan Plateau. We have a glaciation roughly between these two. So at around 0.5 million years, the Tibetan Plateau into an interglacial period when large amounts of melted water flow down the steep slope mountain and converge into the basin, deposit huge amount of sediment. So this is the sediment deposit during the interglacial period. So, well, how do we know whether our results are right or not? We need to compare. This is the elevation map with the present topography from Google Earth, and this is our model's topography. We can compare with the the legend here it's quite comparable. So our simulation, the final topography and the current topography from Google Earth is quite similar. But in terms of sediment supply, sediment deposit, this aspect map of our simulated area in the Cham Basin, they compare with the known sediment thickness from boreholes and seismic. So again, it's quite comparable between the two. So our model clearly reproduce this basin sediment, also topography in both aspects. So now we're going to discuss, so we know, as I mentioned earlier, so one of the things we use the model is to try to work sort to think and quantify these things. From a simulation, we can quantitatively determine the contribution from sediment from the Altai Mountains to the Chitan Basin is only accounted for 14.37%. But roughly similar contribution from the northern ranges, the Chilean Basin, is accounted for 42.95%, and from the Eastern Quaternary Mountain, around 42.68%. So clearly, this have never been done before. So we know not only know exactly how much sediment has been dumped into the basin and the tectonic sediment evolution, but also we know the contribution from each provenance into this basin. So this is the good thing with the bedland modeling. We know in any given seal, we know the sediment, the fate, and also the source to sink. So let's look at the other part. Well, if you look at the Cham Basin, we look at the deposition and also erosion. So this one, we use the time series from right from start of simulation 2.5 million years to present. It's a cumulative, okay? What we see here, the red dot line is the maximum erosion because we have many seals in this basin. So this is the maximum, and this line represents the average, and the dashed line here is a quarter and three-quarter erosion. So basically, the average erosion is roughly in this line. But because of the variabilities, there are certain parts of the basin also got up to 800 meter erosion. Let's look at deposition. With this, again, we use this average deposition. This is also cumulative. In this basin, on the average, we have 800 meter deposition, but in some parts, we would have over 3,000 meter deposition. So it's big variabilities here. So in this basin. If you look at the erosion and denudation of different mountain sections, the Chilean mountain is from the initial simulation to the end. So we see the erosion up to 200 on average, but it can be maximum up to 2,000 meters. For the deposition, because this area is intermountain basins, as the can got an initial deposition, then erosion. So, but on average, the deposition within the Chilean mountain is only 100 meters because it's erosion areas, not deposition. The same thing would be true for the Altai mountain. The erosion, the maximum erosion up to 2,000 meters, but the average is around 400 meters. The deposition, again, on average, is only 100 meter deposition. For the Quaternary mountains, we can see the erosion, the maximum erosion up to 2,000 meters, but the average is 200 to 300 meters. For the deposition of Quaternary mountain, again, we can see it's roughly no more than 200 meter deposition within the mountain. So this is a summary chart that I want to show. This I will probably spend a couple of minutes on this. So in this chart, I want to summarize the deposition of Chitan Basin over time from 2.5 million all the way to present. I will like to draw your particular attention to this region. where, as I mentioned, that the glaciation occurred in the Tibetan Plateau around this region. This is the green. This color is the glacial stage, and this the green is the interglacial stage. What we can see that the erosion of the mountains largely correlated with the interglacial period. So because the ice melting causing denudation of the mountain, and then this subpluvial sediment into the Chedam Basin. Compared with the permanent contribution, as I mentioned, that it's only a small amount contributed from the Altan Basin. So this Altan Basin mainly occur in the early stage of the simulation, but for the late stage, it's remained less than 20%. But initially, it's accounted for 50% because as I mentioned, during the Cheongdam movement B, there is a rapid uplift of the Altan mountains causing deposition. But for the other mountains, like the Quinlan and the Chilan mountains, the contribution since 2.2 million years, it's roughly half and a half, around 42% of the contribution. So through this simulation, we can actually really separate the contribution from each mountain ranges, and also we understand the climate control on the sediments, on the denudation and deposition of this region. So this diagram really sum up all the simulation results that we have done so far. So to conclude, so the geomorphic evolution and the denudation of the Chedam Basin and surrounding mountains has been quantitatively constructed, as shown in the animation. So we find that both tectonic uplift and climate change have exerted significant impact on the denudation and deposition process, the rate, and we can quantify this. The impact varies primarily due to the differential uplift range and also the differential rainfall caused by different geographic locations and the topographic pattern. So mainly, as I mentioned, that the polar and subpolar climate setting. As I mentioned before, the sediment contribution, the prevalence from the Altan, East Quinlan, and Chilean mountains are roughly around 14%, 43%, and 43% respectively. So this actually have shown that such bedland modeling can be used to understand the tectonic sediment evolution history of Petroleum Basin. I hope this will be useful to you when you study in your region in Pakistan in a similar setting. So this actually concludes my talk. Thank you. Any question, please?
Thank you, Professor Liu. A very interesting talk. Now we will take questions from the audience. If somebody have question, please come to the stage.
Hello, my name is Mubashir Khan. I would like to mention that you have delivered a quite comprehensive presentation with a unique approach. My question is that what provoked you? What was the factor that compelled you to use the pi badlands technique? Thank you.
Okay, thanks for your question. So can you hear me? Okay. So as I mentioned before, because I've been working with Tectonic years, so what I found that in the Tibetan Plateau, from many studies, all studies are qualitative and partial. I want to do a comprehensive modeling of the entire basin and the sort to sink, and also to understand and quantify the contribution of sediment. So we found bedland is probably currently the best program that can help us to do that, because it's handled massive evolution, tectonic uplift, and climate. So I think I haven't found any other program so far that can do such large-scale continental simulation. So this is original drug for us using bedland. Thank you.
Okay, another question from Dr. Sanaullah.
Very nice presentation. I have a concern regarding the morphometric your output of this your software which you have used. Just kindly make sure that how hypsometric analysis of that particular basin you have incorporated there in with the whole of the modeling, and what about the maturity of the basin? What factors you have included to estimate the maturity of that basin, sedimentary basin? Thank you.
Okay, thanks. Bedland is a landscape evolution model. So it's simulate large-scale landscape degradation, position, and also the drainage pattern. For detailed geologic simulation, Ahmed Hossein going to give one using citizen for sedimentary simulation that can give a grain size or can simulate carbonate and different grain size. But for bedland, it's only handled one grain size. We use the fishes like shoreline, fluvial, shallow marine fishes, but it's not going to give you any sediment grain size like sandstone, mudstone, siltstone. But for geological modeling, as I mentioned before, Ahmed Hossein is going to give one you can say the same that we can do the sediment fishes changes of the Indus River. I also mentioned for the geology, we try to link G-plate, Tetcom, and others to do the deep process, mental process, convection, dynamic topography, linked to bedland. So we have SC and also up coupled with the precipitation and I hope I answer your question. So I did not catch up your last bit. Thank you.
That was very interesting question from Dr. Snell. We have another question from our guest student. Ramsha, please come.
Thank you, Dr. Liu, for such an informative lecture. I want to ask, as we know, the topography of Tibetan Qinghai is quite complex. So how did you get the current paleotopography of the area?
Okay, thank you. Thank you for the question. So my students are using the DEM model from Google Earth, and then we try to backstrip it. So we actually remove all the center layers based on seismic data, the borehole, to remove the layers, and then to fine-tune using the final thing. So basically start with the Google Earth DM model, and then remove the sediment, and by considering the substance and acidic the loading. So yes, start from present day backstripping, and then forward model. I can't hear you. The microphone is muted.
Well, thank you so much, Doctor, for the talk. I would like to know that apart from the tectonic phases that you mentioned during the basin evolution, so how the climatic records helped in the basin modification and evolution in the particular area? Thank you.
Okay, thank you. Thank you for the question. For the modern area, for the climate impact, basically is the glacial interglacial periods. So we found that during the modeling, the controlling factor for the denudation is actually the precipitation during the interglacial. When the ice melt, it produces a huge amount of water. It can denudate the mountain ranges, provide sediment into the basin. So we're using the marine isotope stages, the curve. So basically, the climate have a significant contribution to the precipitation and the drainage, and thus the deposition as well. Okay, thanks.
Fourth year student. Thank you so much for your enlightening lecture. I want to ask you, as we know that the early Eocene have increased climatic conditions, but lower Holocene have decreased climatic conditions. Why this difference becomes so abruptly in a very short time? And my second question is, how it influenced the Asian monsoon and the source of Indus Basin that was the part of Tibetan Plateau?
Okay, thanks. I think for the climate change, we know that climate is controlled by the orbital change of the Earth. Milan-Curvature curve, we know the Milan-Curvature cycle have many different frequencies. 400,000 years, 100,000 years, 40,000 years, 10,000 years, or even less. So all the changes are based on the Milan-Curvature cycle frequency, astronomy frequency, the causing climate change. In our modeling, we're using the marine isotope stages that actually reflect the Milan-Curvature astronomy cycle. So it's basically it's a different variety of multi-scale fluctuation. So you can have long-term climate change, and then you have a high frequency climate change, such like in the Holocene. It's only 10,000 years. Now the last glacial maximum is around 18,000 years. So basically, this is probably a high frequency climate change, but on a large scale, we're talking about 100,000 years cycle, or sometimes 400,000 year cycle. Okay, thank you.
Thank you, Dr. Liu, for such a nice talk. My Dr. Saab. My question is, how much the uplift of Tibetan Plateau impacted the sediment supply in the Himalayan fold?
Sorry, your voice is low. Can you repeat the last bit? Sorry, I didn't.
How much the uplift of Tibetan Plateau impacted the sediment supply in the Himalayan fold?
The more the supply to the Chinese
from the south of Tibetan Plateau.
Yeah, I tried to. I didn't catch up clearly, but I rephrase your question. Is you mentioned about the present descent supply to the China Basin?
Sir, my question is, how might the uplift of Tibetan Plateau is impacting the sediment supply in the Himalayan fold?
Oh.
As the Indus River is basically originating from the southern part of Tibet. So definitely it will carry the sediments of Tibetan Plateau which are being deposited in the Himalayan fold. Thank you.
Yeah, thanks. Thanks. Okay, I got your question. So yes, I think the area model is in the northeastern part of Tibetan Plateau. So well, I did not model that part, the southern part. I mean, this could be applied. I mean, as I demonstrated, you know, if any student from Pakistan would like to take the Badland model to model the southern part of the Tibetan Plateau and all the salt-to-sink change, salt-to-sink, that'd be great. So I did not model that part. I would think that certainly it can be done. So so that part, I think my students, Ahmed Hossein, probably did not. Well, we did some modeling in Sediment, but we didn't use Badland to do the modeling. I think it can be done by another project. I didn't do this part. Okay.
Now we will take questions from the virtual audience. First of all, I will invite Professor Subrata Ghosh. Please take your question.
Can you hear me?
Yes, we can hear you.
Okay. Thank you very much, Professor Liu. It was a very enlightening lecture. You dealt with so many aspects to find out the evolutionary trend of Chidam Basin. Now, I have three small questions. Three questions. One, how did you exactly determine the ages of different events? Specifically, because you are dealing with very young, only a few, only 3 million years younger than that. How did you specifically identify the ages so correctly? That is one question. Second is, you very nicely quantified the contributions from the three mountains, one from north, one from south, and one from west of Chidam Basin. Now, to me, it appears that the line of contact between the northern and southern mountain and the Chidam Basin is very long. And the line of contact with the western mountain, the Altun mountain, is very short. So if we assume that the contribution may come in the same rate, naturally the northern mountains and the southern mountains will give higher supply, whereas the western mountain will give lower supply. That is a common sense approach. So it's matching very well with your findings. That is second aspect. The third aspect is particularly in the younger time, you found that erosion and deposition, they are going together at high rate at certain times, and at certain times erosion is more than deposition. So why that discrepancy? That is another question. Is it
okay,
clear?
thank you. Yeah, thank you for your questions. Yeah.
Thank you.
The first one, for the ages, we use a number of techniques. Like for the younger one, we use the latest one use radiocarbon dating. Lots of ages we base on the planation surfaces and river terrace. Also, we using to date the TL, using TL data of the gravels and other things. In other part, we also have some, we correlate with the marine isotope stages using other techniques. So that was an issue. And also there are some like bigger faunas and also plant fossils, pollen, spawned pollen in the region. For cell question, yes. Certainly, one of the key things we want to do the modeling is we want to understand the salt sink, the respective contribution quantitatively from each basin. Your analysis is perfect, correct. The one thing I want to mention, add to that, because the Ertin mountain was uplifted rapidly at the early Pleistocene around 2.4 million years. Then it's become inactive. That's why we only have an initial big contribution from the Altai mountain from the west, while the northern Chilean mountain and the southern Quaternary mountain contribute quite a bit, nearly 40% each. For your third question, yes, in my analysis, we have deposition and erosion at the same time. So I need to make clear, because some of the mass plot is the average of the entire basin. Like I see Chilean basin, we probably have 10,000 cells. We have the average and also maximum minimum. We have a 3/4 and also the average. So in the mountain range, sometimes we initially have a deposit and then this part would be eroded later on. So you would have an initial high deposition, then the cumulative become less and less with time. But it's the heterogeneity in the basin. In the basin, you have certain part got lots of erosion at one time, then depositing in the deep part of the basin. When we do the average, you would have a large variability. I hope this answers your question. But the curve you need to be see as an average of the entire basin or entire mountain range. But we have all the data for each cell. For each cell, we have the detailed mountain information we can extract if we want. Yes. Hello, can someone hear me?
Question from Professor Bosch. Now the next question is from Dr. Mumtaz Shah. Please turn on your mic.
Yeah, thank you, Dr. Jawad, and thank you, Professor Liu. Nice to see you after a long time.
Yeah, hello.
Yeah, we see last time in Wuhan.
Yeah.
It was a very informative talk. Really enjoyed this this talk which you have presented, although I was a bit late to join you because of some classes. And secondly, the question is that you talked about this forward stratigraphic modeling, which is nowadays very key in terms of better understanding the basin architecture in areas like in Pakistan, where this stratigraphic modeling is very new for us. I would like to know that how much tricky is to model a particular basin which is tectonically complex. Like in Pakistan, we have the northern part of Pakistan where we have the upper Indus Basin, which have complex tectonics, and how we can be able to better model using this forward stratigraphic modeling technique using different software, TAMIS 3D or some other softwares which are normally being used. Yeah, thank you, Professor Liu.
Okay, thanks for the question. So yes, we use quite a lot of forward stratigraphic modeling. Currently, we also write a book chapter with people from Stanford on combining basin modeling and with the forward stratigraphic modeling. So actually, I got one paper in this year's AEPG. So we described a coupled modeling between Petroleum mode and Sediment. So yes, you can model a basin with a complex tectonic history, but you need to model probably layer by layer. So you can't model the whole basin, but if you have a targeted reservoir, you want to understand the phase changes within this reservoir, you need to restore the initial surface and then run the model. Then you can put the model into Petrol or sometimes petro mode, you can actually using the output from a fault structure modeling to help you to the reservoir modeling or basin modeling. So you have to do two steps. You can't do the whole thing in one go. You have to do separately.
Thank you very much, Professor Liu. Thank you very much, Professor Liu. It was a very good lecture and we learned a lot. We are also interested in the region of the sediments, especially Tipton Plateau, as it is shedding load to the Indus River. And I again thank you. We will now take a break for about 1 hour, and then we will come back at 2:30 Pakistan time. And then there is a lecture from your student, Hafiz Raza. So I think you will attend that lecture. And I thank you, all the audience, and hope they will again join us at 2:30. Thank you very much.